This footage shows a column of fire shooting up from a gas well in Uzbekistan. The blaze ignited due to a leak and lasted 1,064 days. The Soviets tried everything to turn off or divert the well, but these efforts only provoked new, smaller blowouts in different locations. It seemed that nothing could stop the raging fire. That is, until the Soviets decided to take an unconventional approach, to nuke the well. Nuclear bombs are commonly thought of as only serving one purpose, to cause mass destruction. Yet in the 1960s, both world superpowers conducted several tests that considered alternative, peaceful applications. With acclimating and ever-increasing stockpiles in the US and USSR, the countries began assessing whether the weapons could be put to good use rather than just have them standing by. Soon enough, the United States started Operation Plowshare to assess whether nuclear arms could be employed for excavation or natural gas fracturing. Most tests for these operations were conducted in the Nevada desert over 20 years between 1958 and 1975, leaving behind a number of craters. The Soviet Union implemented its own program called Nuclear Explosions for the National Economy. This also focused primarily on practical applications in mining and extraction of natural gas. However, one significant difference is that the US preoccupied itself with the environmental effect of the tests. It was an aspect that the Soviets almost completely neglected, and the USSR made some questionable decisions. One test contaminated a highly populated area along the Volga River. They even used a nuclear bomb to create a reservoir by bombing another river, an act that carries radioactive consequences to this day. During the research into these new unconventional uses of nuclear weapons, scientists in both countries began to conceptualize solving other problems with peaceful nukes. These included shutting down oil and gas leaks and capping dangerous volcanic activity. The fire in question started when a well in southern Uzbekistan suffered from unexpected blowout in 1963. The blast occurred at a depth of 2.4 kilometers underground. The escaping natural gas shot out of the ground in a column of fire that burned reliably for nearly 3 years and released about 12 million cubic meters of the valuable fossil fuel each day. With the daily output of the leak, the Soviets could have fueled some cities, making the issue of the blowout even more frustrating. No one in the Soviet Union knew how to put out such a complex fire. At a point of absolute desperation, the Soviets began considering whether dropping a nuclear bomb at the site would be a feasible and functional way of dealing with the issue. Scientists, officials, and engineers set to work on a concept for what nuking the area would look like. Physicists estimated that detonating a bomb at a depth of 1,500 meters could close the shaft, while the pressure caused could cut off the fire. Furthermore, 30 kilotons, double the power of the Little Boy bomb dropped on Hiroshima, would be needed for a successful operation. The operation would be conducted in the fall of 1966. The area was in a desert environment, meaning that any mishaps would hopefully have few consequences for civilians. The field at Urtabulak was at least 100 miles from the nearest developed area, the southeast of Bukhara. By then, the heat of the burning fire had carved out a considerable crater in the desert sand. After calculating the necessary depth and strength of the bomb, officials determined that a nuclear blast would not only stop the fire, but it would be the best option. They first had 2 boreholes drilled down to the blowout area, placing a tube through which they could carry the bomb down to a depth of 1.4 kilometers. A 30-kiloton nuke was lowered down one of the boreholes, and the well was filled up with cement to prevent radiation from escaping. The whole experiment was captured on film. Details of the operation were recounted in the Soviet newspaper Pravda Vostoka of Tashkent, which is located in Uzbekistan. Of the event, the newspaper published the following, quote, "On that cold autumn day in 1966, an underground tremor of unprecedented force shook the ground with a sparse grass cover on white sand. A dusty haze rose over the desert. The orange-colored torch of the blazing well diminished, first slowly, then more rapidly, until it flickered and finally died out. For the first time in 1,064 days, quiet descended on the area. The jet-like roar of the gas well had been silenced." It took about 20 seconds for the fire to be extinguished by the nuclear explosion. The Soviet engineers had managed to use the nuke successfully and eliminate a 3-year-long problem. It's generally agreed upon that this was the first experiment of that nature. Furthermore, upon sharing the information with the United States, the occasion marked the first time they shared the exact location of a nuclear blast. This would not be the only instance where the Soviets were able to test their technology in such a way. A few months after the Uzbekistan gas leak was sealed, another fire broke out at the nearby Pamuk field, shooting flames through several boreholes. To stop that fire, engineers opted to send a 47-kiloton bomb 2.44 kilometers into the ground, following a similar protocol. The second experiment was a success as well. Russia is thought to have used a technique at least 5 times. Eventually, a Soviet weapons lab developed a specific nuclear bomb intended to close holes between 82 and 164 meters away from the blast. Project Kanakyn was part of a series of nuclear tests aimed at testing the effects of underground nuclear detonations that dated back to the early 1960s. This top-secret American operation aimed to test the powerful LM-49 Spartan anti-ballistic missile. Previous detonations had taken place at Amchitka Island in Alaska, but none would be as destructive as the Kanakyn nuclear explosion. On November 6, 1971, one of the world's most powerful nuclear warheads was placed in a hole some 6,000 feet below the ground. The island had been evacuated, and while the project's personnel impatiently waited for President Richard Nixon's approval, a small group of civilians headed towards the island in a heroic attempt to stop the proceedings. However, it was too late. Amchitka is the southernmost link of the Aleutian Island chain and extends from the Bering Sea in North America to the Russian coast. The native Aleut population that once roamed this island made contact with Russian fur traders during the 1760s and was slowly banished less than a century later. Many fell to diseases, while others were displaced to work at colonies established by Russian and American colonizers. Then, during the gold rush that swept through Alaska, U.S. President William Howard Taft signed an executive order that set aside the entire Aleutian Islands as a wildlife reservation. Nevertheless, the executive order left loopholes for economic and military exploitation. Following the Japanese bombing raids of Dutch Harbor and the subsequent occupation of the islands of Attu and Kiska, the U.S. Army moved into Amchitka in 1942 to establish forward positions and repulse the Japanese if they decided to engage once more. The military then built a landing strip and a dock, with over 16,000 servicemen relocated to the island until the end of the war. The island of Amchitka was briefly allowed to rest for wildlife conservation once the military abandoned the outposts. However, in 1950, amid the Cold War and the outbreak of hostilities in the Korean Peninsula, the American Atomic Energy Commission began to consider the island as the possible testing ground for future nuclear ordnance. The ongoing arms race between the Soviet Union and the United States led to the rapid development of powerful nuclear devices that were up to 5 times more powerful than the atomic detonations of Hiroshima and Nagasaki. Both nations conducted several secret nuclear tests that increased in power with each new prototype, and scientists realized that adequate seismological knowledge was critical for detecting Soviet nuclear explosions. Several nuclear bombs were then detonated in the Nevada desert to study seismic signals as part of Operation Plum Bomb in 1957. However, the results were disappointing, and in 1959, Dr. James R. Killian formed the Panel in Seismic Improvement, intending to improve the development and deployment of seismic instruments and study the seismic effects of nuclear explosions. This led to the establishment of the Vela program, or Vela Uniform, a joint project between the Department of Energy, the Atomic Energy Commission, and the Advanced Research Projects Agency. The Vela Uniform would conduct 7 underground nuclear tests in the continental U.S. and Alaska between 1963 and 1971 to study seismic traces with high explosive ordnance, and Amchitka was one of the locations. Amchitka was occupied by the Department of Defense in early 1960, and hundreds of scientists from numerous laboratories and atomic commissions set up infrastructure to measure the nuclear weapons that would be detonated. The Atomic Commission announced that the goal was, quote, to determine the behavior and characteristics of seismic signals generated by nuclear detonations, and to differentiate them from seismic signals generated by naturally occurring earthquakes. Then, on October 29, 1965, the long-shot nuclear bomb was detonated below the ground on Amchitka's surface. The bomb yielded 80 kilotons, and although the surface did not collapse, krypton and tritium were later found near the area. As civilian unrest grew with the Vietnam War, protesters began to protest the war and the ongoing nuclear tests. Still, President Richard Nixon approved the detonation of another bomb as part of Test Milrow. According to a documentary from the Department of Defense, Milrow's purpose was to, quote, test an island, not a weapon. The bomb was detonated on October 2, 1969, and had a yield of 1.2 megatons. Footage from the time shows how engineers drilled a 4,000-foot shaft into Amchitka's surface to lower the bomb and detonate it from below. Milrau's shockwave reached the island's surface with an acceleration of 340 square meters per second, and footage taken by the Department of Defense shows how it created a dome on the island of approximately 2 miles in radius, with a height of about 16 feet. Additionally, the DoD films show how the blast, quote, turned the surrounding sea to froth and forced geysers of mud and water 50 feet into the air. Despite the damage from Milrau, it would prove nothing more than a mere warm-up for what was to come. Following the Milrau test, environmental activists formed a committee in Vancouver to put an end to the nuclear tests in the Aleutians. Besides the fear of environmental contamination, they believed further tests would cause earthquakes and tsunamis. This committee eventually led to the creation of the Greenpeace organization. Still, the DoD and the Atomic Energy Commission decided to carry on with Project Kaneken as part of the Vela uniform. This project's objective was to test the design of the LM-49 Spartan anti-ballistic missile, or ABM interceptor. The missile carried a W-71 warhead, a high-yield warhead that produced huge amounts of X-rays, debris, and fission output to prevent the blackout of ABM radar systems. Footage from the Department of Energy Nevada Operations Office shows how over 400 tons of equipment had to be placed in a shaft that was over 6,200 feet deep and over 90 inches wide. In addition, engineers used a new alignment laser to make a deep hole into the island's rock. The video then shows how the engineers lowered the gigantic Spartan missile with its 5-megaton warhead into a vast chamber located at the bottom of the shaft. Following the Spartan missile, the engineers lower a 264-foot-long instrumentation package linked to a fleet of truck trailers stationed half a mile away. All of the surrounding test support equipment was specifically designed to survive a ground upheaval of around 15 feet, including the test electronics and the field recording computer. While the DoD and the AEC prepared the nuclear detonation, the Greenpeace activists who had taken to the sea in an effort to stop the test had to abandon their mission after winds that topped 125 miles an hour forced them back. With nothing to hold him back, President Nixon finally gave the green light for the missile's detonation on November 6, 1971. Project Kaneken became the largest underground nuclear test ever conducted by the U.S. It was so powerful that it comprised over 14% of the total yield generated by all 730 underground tests that have been undertaken by the country. The blast registered a seismic shock of 7 on the Richter scale and left a crater over 60 feet deep and 1 mile wide. The crater was quickly filled with water and became the largest lake on the island. Footage taken from a helicopter captured the scale of destruction as lakes, ponds, soil, and infrastructure soared into the air up to 15 feet, while seabirds, thousands of sea otters, over 10,000 sticklebacks, 700 Dolly Varden, and hundreds of harlequin ducks did not survive the shockwave. Following the Kaneken detonation, Amchitka was never used again by the U.S., and a 1996 test from Greenpeace found that there were traces of plutonium, americium, and other chemicals on the island. To this day, the island has not recovered from the effects of the nuclear detonation, and the footage clearly shows how the island's landscape was forever changed. Still, the test was considered a resounding success, as scientists were able to gather plenty of information from the warhead's performance and found that the blast had no radioactivity at all. Years later, the U.S. would continue performing nuclear tests at the Nevada test site by using the intelligence gathered from the Kaneken explosion. For decades, there's only been one conventional weapon capable of completely destroying an enemy warship in a single hit: the torpedo. Still, recent footage taken by the U.S. Air Force shows a new imposing weapon that aims to have the same effect on enemy vessels, but this time, the projectile drops from the sky. The so-called Quicksink bomb is designed as an intelligent and inexpensive solution to engage naval targets with the same destructive power as a torpedo, but with the crucial particularity that it is deployed from a warplane. The eye-opening footage shows a large cargo ship stationed in the Gulf of Mexico, when in a split second, a projectile falls right beside her, exploding underwater. The massive cargo ship is then torn in half by the potent blast in a spectacular display of power, representing a highly significant moment in U.S. military history that could radically transform the future of naval warfare. Torpedoes have been the go-to choice when seeking to disable enemy ships in a quick and reliable way. Other than a few specialized high-yield explosives, the torpedo remains one of the only ways to sink a warship with a single shot. As effective as torpedoes have proven to be, they are an expensive and challenging solution. Major Andrew Swanson, 85th TES Division Chief of Advanced Programs, explained, quote, "Heavyweight torpedoes are effective at sinking large ships, but are expensive and employed by a small portion of naval assets. Because the Navy only has a limited number of ships capable of launching torpedoes, and the devices being so expensive to produce and maintain, the U.S. military has found itself with limited options to swiftly neutralize large ships. To address this issue, the U.S. Air Force, in partnership with the Navy, developed the Quicksink program, which seeks to provide new options to rapidly neutralize naval surface targets at minimal costs, while also demonstrating the intrinsic flexibility of the joint force in combat scenarios. The Quicksink program has already produced a promising first application that might open an entire array of similar solutions for the U.S. military. The initial iteration is a modified 2,000-pound GBU-31 Joint Direct Attack munition altered with a guidance kit that converts the conventional projectile into an intelligent bomb capable of correcting its course. The guidance conversion kits are relatively cheap to produce, and they drastically improve the projectile's accuracy and capabilities. Despite being dropped from above, the bomb is designed to detonate below a ship's hull in order to attain similar results to those of a torpedo. As the projectile is dropped from the aircraft, its guidance system adjusts its course to hit the water just beside the target vessel. Once underwater, the payload detonates below the ship's hull, perforating it or ripping it apart to facilitate the expeditious sinking of the enemy ship. Swanson would further explain the advantages of the new technology, quote, "With Quicksink, we have demonstrated a low-cost and more agile solution that has the potential to be employed by the majority of Air Force combat aircraft, providing combatant commanders and warfighters with more options." The breakthrough provides the U.S. military with an additional solution against naval threats, but it also does it in a more cost-effective way, and with the ability to endow almost any warplane with the destructive power of a torpedo. On April 28, 2022, the U.S. Air Force Research Laboratory and Eglin Air Force Base's Integrated Test Team conducted a test with the preliminary Quicksink bomb. The payload was delivered via an F-15E Strike Eagle, which released the modified 2,000-pound GBU-31 Joint Direct Attack munition over a large cargo ship in the Gulf of Mexico. The test was the second experiment in the Quicksink Joint Capability Technology Demonstration, with the first time taking place at an undisclosed location sometime in the recent past. The April test was a joint effort between the Air Force Research Laboratory, the 780th Test Squadron of the 96th Test Wing, and the 85th Test and Evaluation Squadron of the 53rd Wing, and financed by the Office of the Undersecretary of Defense for Research and Engineering. Colonel Tony Meeks, Director of Air Force Research Laboratory's Munitions Directorate, explained the reason for developing such a weapon, quote, "Quicksink is an answer to the urgent need to neutralize maritime threats to freedom around the world. The men and women in this directorate consistently find ways to solve our nation's greatest challenges." The experiment conducted in April used Joint Direct Attack munitions, a guidance kit that converts unguided bombs into all-weather precision-guided munitions able to adjust their course mid-fall in order to strike the target in the most efficient possible way. In it, the conventional munitions are fitted with a GPS-assisted inertial navigation system, which allows them to identify their exact position in real time, as well as the position of their target. Thus, even if the target is moving, the bomb is able to reach it to deliver its payload. In contrast to torpedoes, which are also capable of sinking ships with a single hit, but often reveal the location of the firing submarine, Quicksink devices leave the deploying aircraft safe from a counterattack, as they can immediately leave the area. Kirk Herzog, the Air Force Research Laboratory Program Manager, elaborated on their goals. Quote, "A Navy submarine has the ability to launch and destroy a ship with a single torpedo at any time. But the Quicksink aims to develop a low-cost method of achieving torpedo-like kills from the air at a much higher rate and over a much larger area." The whole idea boils down to reducing costs and risks, as airdrop payloads make counteroffensives much harder to execute. Even if the target is able to successfully engage the warplane, its crew is smaller and might be able to escape. In contrast, a submarine crew might suffer more severe losses. Furthermore, a single F-15EX aircraft costs $87.7 million, whereas a U.S. submarine can cost up to $2.8 billion per unit, making submarine torpedo attacks even riskier and potentially more costly than the Quicksink solution. The footage released by the U.S. military shows the empty cargo ship floating in the middle of the Gulf of Mexico. A joint direct attack munition then drops from the sky right beside the old cargo ship. The bomb seems to burst just below the waterline, releasing the blast underneath the ship where her armor is the lightest. The explosion immediately splits the vessel in half as she sinks in fractions of a minute. Had the explosive hit the deck instead of the ship's underbelly, an immediate sinking would have been less likely, as decks tend to be heavily reinforced and the ships are often able to continue operating. Thus, the novel technology has taken everything that makes a torpedo so effective and lethal to enemy ships and applied it to an airborne solution, drastically reducing the costs of deployment as well as the risk to the lives of U.S. servicemen, while retaining the impressive power that can sink a ship in just a few seconds. If the program continues to thrive, many other types of quick-sink solutions will emerge, polished for different combat scenarios and fine-tuned to counter specific maritime threats. From April to August of 1958, the United States detonated as many nuclear bombs in the Pacific Proving Grounds as had been fired in all prior tests in the region. One of them was the massive Umbrella nuclear blast that took place in Bikini Lagoon on June 9th. The 8-kiloton underwater explosion was part of a major series of nuclear experiments known as Operation Hardtack, which was not merely concerned with the development of atomic weapons. Impressive footage from the event shows a colossal column rising into the skies and reaching a top height of 5,000 feet only 20 seconds after detonation. Indeed, the test had given both the Department of Defense and the Atomic Energy Commission a vital clue, not only about the weapons, but also about radioactivity and its consequences, and it was not what they had expected. Operation Hardtack 1 took place between April 28th and August 18th of 1958 and was directed by Joint Task Force 7, a collaboration between military and civilian parties. However, it was structured like a military organization. Joint Task Force 7 was composed of 19,100 personnel from the U.S. Armed Forces, federal civilian employees, and workers affiliated with both the Department of Defense and the Atomic Energy Commission. While the operation would see an immense amount of shots, the scale of the enterprise was not as relevant as its variety. During the tests, many different weapons were evaluated across land and water surface trials, underwater and balloon detonations, and also rocket-borne high-altitude experiments. The entire enterprise was divided into 3 parts. First, as a continuation of the tests that had taken place at Amchitka and Bikini through the early and mid-1950s, which aimed at the development of ever-better nuclear weapons. During those tests, the Los Alamos Scientific Laboratory and the University of California Radiation Laboratory, both from the Atomic Energy Commission, or AEC, detonated several experimental devices with the support of the Department of Defense. The second part was sponsored by the DoD. It consisted of underwater test shots with the purpose of improving the understanding of the effects of underwater explosions on Navy assets, from ships to the material. In truth, this phase could be considered a direct continuation of Operation Crossroads and the Baker underwater detonation at Bikini Atoll in 1946, which was followed by the Wigwam test off the U.S. West Coast in 1955. Finally, the last part would deal with a previously unknown military issue: the deployment of nuclear weapons in air and ballistic missile defense. As such, Hardtack 1 employed a range of weapons directed towards this objective, including rocket-borne high-altitude explosions and a balloon at 86,000 feet over the gap between Amchitka and Bikini. As a continuation of the Baker tests in Bikini Lagoon, the Department of Defense oversaw the second phase of Hardtack 1, which consisted of 2 separate trials. The first, codenamed Wahoo, was an underwater detonation in the open ocean. The second one, known as Umbrella, took place in the lagoon inside Amchitka. Of high importance was that explosions in shallow water can create craters if they happen close enough to the bottom. The same ships used in the Wahoo test were towed into the region to be reutilized for Umbrella. Indeed, the damage caused by the first detonation was minor in all cases, except for a single ship, Moran, which required her hull to be refurbished. Still, all ships had to be washed down, and their measuring equipment was replaced before use. Meanwhile, the mooring for Umbrella was significantly easier than for the first test in the open ocean, and the location and depth of the lagoon greatly facilitated the process. Evidently, the information gathered from the Wahoo test was directly implemented in the following experiment, and it affected the arrangement of the targets as well as decontamination times. Only then was the device placed, by means of a buoy at a depth of 150 feet. On June 9th, the second underwater detonation of the series and the 14th test overall kicked off. As captured on camera at the exact moment of detonation, the explosion occurred at 11:15 a.m. under clear skies. The wind was from 17 to 20 miles per hour, coming from the east-northeast. In only 1/10 of a second, a dome of spray broke through the surface and created a column in the air. The 8-kiloton explosion launched the vertical shape 5,000 feet into the air, reaching its top height 20 seconds after detonation. Meanwhile, the surge spread across 10,000 feet downwind at its base and reached no less than 6,000 feet in all directions. The base surge could be observed from the air as long as 25 minutes afterward. Notably, the foam patch that formed over the blast location lasted even longer. Umbrella pierced through the sandbed at the bottom of the lagoon, and its blast created a crater of 3,000 feet in diameter and 20 feet in depth. And the maximum radiation reading was 0.350 Röntgen per hour, as measured by an aircraft overflying the spot. It is said that radiation was found in small portions, and thus re-entry permission was granted only half an hour after the detonation. The tests required device placement techniques and data recording operations that were new to nuclear weapons testing. Central to the series, the testing program and its specific requirements called for a particular form of organization and personnel participation. The program had 2 main aspects. First, the weapons development, and then the measurement of the explosion and the after effects. Moreover, Hardtack 1 incorporated test operations that supported each element separately, unlike earlier nuclear experiments. The 2 approaches also differentiated the main interests of the major participants. For one, the AEC was focused on weapon development, while the DoD sought to investigate the military applications of the explosions and their effects. Still, each part of the long development process and the studies included the inherent risk of radiation exposure. Following Umbrella, the highest radiation level was logged at 0.0015 Röntgen per hour in the stern of the Moran merchant marine ship. Subsequently, all scientific data was gathered from the target vessels, and only then were they restored to seaworthy conditions and towed back home to Pearl Harbor. However, Moran was deemed unseaworthy and had to be sunk by naval gunfire near the island of Ikrin. Both underwater tests gathered significant evidence that significantly helped the DoD understand the effects of nuclear weapons on Navy ships. Among the most interesting points was that underwater tests create less fallout due to the absorption of radioactive material in the water and vaporized droplets. In addition, direct gamma radiation was found to be extremely low, although the base surge was highly radioactive, followed by waves of smaller radiation concentrations that mimicked that initial base surge. After 15 minutes, almost all free-field radiation activity was found to disappear, and thus they were allowed to return to normal operations. On the other hand, the impact of the shock waves was impressively lower than expected. In truth, the shock wave was considered negligible on the destroyers at the tested ranges. Nevertheless, the equipment failure that resulted from the blast did immobilize the ships. In conclusion, the results showed that the preliminary tests of explosive tapered charges simulated the shock waves launched by a nuclear device.